Good afternoon, ladies and gentlemen. This tutorial introduces some of the specific requirements for timing and synchronization in defense application. We will introduce crucial expectation for military that drives constraint on time and synchronization appliance. We will then define different support systems that needs timing and synchronization. Then we focus on the environment and threat that time and synchronization systems that cope with. Finally, we present some technologies that contribute to answer to the defense application challenge. Efficiency of defense forces are based on the proper coordination of task force that enable optimizing impact on the adverse deployment. The coordination is effective only if information about the situation is caught and transferred promptly to a central place of analysis. The knowledge of status of cooperative versus enemy force is key for setting action plan to act against threat. Crucial technical vectors, fostering tactical awareness and piloting task forces in contact with enemy remain on technical vector powered by time and synchronization. Secure captured information. The aim is to capture trustable information and be able to correlate and cross-check them with consistent time tag. Enable secure communication. The key enabler is the ability to maintain communication channel between all components of blue forces. The communication shall be secure to protect data integrity and privacy. Build consistent situation management. When assembling information of different types and various origin, consistency is depending on aligned time reference for time tag attached to each information. Time synchronized action leads to maximize impact against threat. Let me introduce some military task support system that need timing and synchronization to work properly. Capturing tactical data information, airborne sensor are cost-effective solutions that maximize covered area for multiple types of information: magnetic anomaly, radio communication, radar, infrared, optical, LIDAR. The high altitude enlarge the area coverage. The carrier mobility also widens the vision span and enable to rebuild a large area mapping, thanks to accurate position and timing of the platform. Accuracy is key to optimize computing power when building situation map from multiple instant picture. Second important pillar is the ability to maintain communication paths with agile and or isolated platform. Radio frequency communication is the only way to do the job. Symmetrically, that's where enemy usually concentrate interception capabilities or denial tasks, using jammer and spoofer to block or deceive communication. Technologies developed to counteract communication sensitivity are multiple. First one is extending CDMA civil technologies with maximizing code rate. It enables to increase signal to jammer ratio. To counter interception in the communication path, CDMA can be improved with the use of secret aperiodic code for multiplexing rather than known periodic code. Such codes are generated with a secret function that rely on private key combined with time of day to create a unique sequence of number. Switching at fast pace the frequency channel used in a technique is a technique to deceive radio frequency threat. Emitters and receiver need to share the same table of frequency sequence and the same time of switching. Frequency sequence is generated with an aperiodic time-dependent function. To enable long silent sequence, an accurate and synchronized clock shall feed each communication link. Concentrating radio frequency power in the known direction of receiver is another technique that improves signal per jammer ratio. Knowledge of position, attitude, and trajectory evolution over time is necessary to maintain antenna pointing. When communication path is effective, data can flow bottom-up and top-down. However, data shall be protected to maintain their integrity and privacy. To detect insertion of malicious data into dataset, a signature is included. The signature authenticates data source. Signature is based on asymmetric key encryption scheme, including time of validity in the signature, increase authentication scheme. To protect privacy of data, Crypto function is scrambling information with a function using secret key. Aperiodic functions using both secret key and time of issue overprotect data when transitioning on radio frequency where probability of interception is not low enough regarding the level of secret. The third pillar is the ability to build global situation awareness and pilot coordinated action. Situation awareness is shaped from aggregation of information from multiple systems. To accelerate fusion, time tag shall be consistent from the different system sourcing. Any time difference can make significant distortion in the vision delivered to the decision-making team. Then, execution of action shall be properly synchronized. Command staff rely on coordination of mobilized resources to optimize power effect against threat. On the local area, fire synchronization increased stupefaction on adverse forces. At battlefield level, correlated strikes are maximizing the impact. At theater level, joint forces land, sea, air, and space unable to saturate enemy capabilities, disabling efficient response. Finally, area conservation or conquering is dedicated to soldiers. Fire sustaining of blue forces need accurate tracking of identification of friend or foe that avoid friend strike and enable close combat support. IFF systems are using radio frequency communication with secure scheme. Considering all applications, timing request is characterized with the time accuracy to command reference. Ranked by increasing time accuracy request, applications are consistent timestamping of data for massive fusion, geospatial correlation of time with position and attitude, crypto protection and authentication, communication channel resilience through antenna pointing, card multiplexing, frequency hopping. Time accuracy requested is from 1 second for coordination to microsecond for crypto protection and topping to 1 nanosecond for time of arrival based location. Frequency synchronization is supporting common information carrier, especially in frequency hopping scheme. Synchronization of emitter and receiver help increase silence interval. It also drives the autonomy of the local clock for communication and navigation. Relative frequency accuracy span between 10-7 to 10-11. Requested timing and synchronization performances are at the same level for the civil application, but there is a unique dimension that differentiates its environment. Defense application special is dedicated to work in hostile environment. Wartime is characterized by denial of rules and breaking of limits. It results that appliance shall withstand with harsh physical environment. Environment can be altered on purpose by enemy, heat, strong electromagnetic disturbance, nuclear radiation. Electronic equipment shall prove to be resilient. It shall sustain performance to follow on mission. It shall be able to recover from hard strike and perform again. The master word for military platform is mobility is the key for survival. That's why timing and synchronization appliance need to sustain vibration, shock, acceleration, attitude flip, extended temperature range, limited size, weight, and power consumption. Let's focus on threat and show technologies that are developed to mitigate their impact. Through radio frequency spectrum, mobile clock systems need to acquire external common reference to be aligned with other clocks. In open field, GNSS signals offer worldwide coverage and very accurate time for which can be derived very accurate frequency. Soldiers, land vehicle, air carrier, ships can receive and use GNSS signal everywhere. However, hiding constraint drive sometimes to canyon or shaded area where the high frequency signal line of sight is obstructed. In that case, internal frequency reference shall maintain time accuracy. In order to maintain confidence with GNSS signal capture, the signal acquisition shall protect from interference generated from out-of-band or multipath GNSS signals that overlap with weak GNSS signal. Increasing error associated with the timing solution, GNSS military services provide higher bandwidth spread spectrum codes. It increases decoded carrier to interference power ratio. Time receiver autonomous integrity monitoring, coupled with stable internal frequency reference, selects signals that are only delivering likely solution regarding recent past and local sensor information. So it minimizes risk for the solution to be steered to unlikely signals. Intentional jamming is usual threat on fighting area. Specific detection are inserted in the GNSS receiver. It informs the platform about attempts to the service access. It also may tune dedicated filtering in the frequency or spatial domain. Most sophisticated threats like spoofing are specifically targeting to provide fake PNT solution. Detection of such signals, which are very close to good ones, need to be include intelligence inside the receiver. Close comparison between signals and integrity check with embedded sensors raise probability of detection. Detection provides information for switching to local reference. It can also tune specific reprocessing of GNSS signal that discard suspicious signals and build mitigated solution. Here is an example of the sophisticated detection of interference, jamming, and spoofing. It uses existing GNSS receiver filtering and processing capabilities. Non-standard parameter comparison and evolution are feeding the detection algorithm. It builds a scorecard that is compared to a fixed threshold. It shall maximize false alarm rate and at the same time maintain an effective level of probability of detection. On the bottom of the window, it shows instantaneous spectral power on the GNSS analyzed band. On top is the evolution of the process scorecard over time. Blue drawing is scorecard about jamming, green drawing is about spoofing. The red drawing is figuring the alarm threshold unified for both scores. On the left picture, a jamming very narrow band and far from center band of interest signal is providing weak spoofing score as well as moderate jamming score that are both under threshold. It doesn't prevent the receiver from computing a valid PNT solution. On the right picture, a more powerful jammer with larger band and in-band centered is disturbing GNSS signal computation. The spoofing score is under threshold, while the jamming score is well over. The detection algorithm is issuing an alert to the clock system. So the clock system switches to another source and maintains previously acquired solution with holdover. Active filtering is providing mitigation to attempt cleaning up the signal in GNSS band. Adaptive versatile large filter can significantly attenuate jammer or interference power in the signal processing. For spoofing deception, comparison of different processes applied on the same signal in different correlators can sort out between suspected signal and safe one. This plot of the evolution of average all in-view satellite carrier to noise when a jammer ramps up in power and when vanishes. Jammer is characterized by green trace. The red trace is a plot of a standard GNSS receiver integrated state-of-the-art receiver autonomous integrity monitoring with no mitigation. The receiver is not able to maintain true signal extraction when jammer power exceeds 1.6 times A dB. When jammer power decreases, it only recovers a little before jammer power going close to A dB. The blue trace plot the output of the same receiver with injected signal pre-filtered and reprocessed at correlator's internal filter. It shows an improvement of protection, expanding the capability to process true signal with 1.3 times a higher powered jammer. When applied on the field, such mitigation technology has a drastic impact on the resilience to jammer or spoofer. A 100-watt radiated in-band of fossil jammer on air carrier can deny standard GNSS receiver services up to 100 km radius from emission point. When applying active filtering, mitigation can lower disturbance distance to a few kilometers. Another mitigation technique is spatial filtering. A very cost-effective solution is to replace standard semi-hemispheric antenna that capture open sky all-in-view radio frequency signal with a narrower aperture antenna with privileged gain at zenith. The shown unit is providing more than 12 dB attenuation versus zenith gain for lower than 20-degree elevation. Malicious emissions are usually distant and so elevation angle is low. However, this solution is not applicable for attitude mobility platform. More sophisticated spatial filtering is achieved by combination of multiple radio frequency antenna elements forming a CRPA. The combination of signals from each single antenna elements create directional constellation of signals or directive narrow beam. Such antennas are more complex. Their directivity is limited by the number of single radio frequency combined and the spatial geometry of elements. Central picture is showing radio frequency gain per azimuth for a very basis 2-element antenna. The right picture shows a simulation of constellation of a jammer figured on the red point. The colored surface is showing global CRPA gain after steering process, with up to 30 dB constellation in the direction of jammer. Hostile harsh environment protection is sensitive for frequency sources. Specific development of dedicated frequency reference is mandatory to reach resilience and sustainability expected. Frequency sources is the key component that feed local autonomy of the clock. Recent development of mini-atomic clocks fits with such constraint. A state-of-the-art mini-rubidium reference can provide resilience to vibration, withstand high peak shock, and maintain low frequency deviation per acceleration. Magnetic field variation is creating low deviation. Mobility is sustained with low size, weight, and power. Thanks to atomic reference, influence of external temperature to relative frequency is lower than 410-10 over 75 Celsius range. Short-term frequency stability measured with Elan deviation over 100 seconds is lower than 410-12. Relative frequency edging, the main driver for long-term stability, is lower than 10-10 per month. It is answering synchronization requests for most of the application, except for very long period of autonomy or top protected radio frequency communication network. Conclusion is that military application request similar level of performances than civil ones, despite technical application may be different. But the difference that make it all is the hostile environment that is much scope with. It's where resiliency, sustainability, and ability to recover is making everything different. Dedicated techniques are developed to assure time and synchronization availability under such constraint. Rugged clock is key component of military platforms. Thank you to ITSF for enabling us to open the window and have an insight out of the civil domain, and thank you for your attention.